Okay, so another common parallel computing paradigm is Dataflow, and this has been around, for a long time. And the idea is that when data values that are required by an operation become available, the operation then, fires, producing new values, which then, fire off maybe additional computations downstream. And but unfortunately, it's been a parallel programming technique which has never really sort of found a place it can run, right? So there was a lot of early work back in the 80s and 90s on data flow machines and data flow systems and functional languages and all the rest of it, but it was never really particularly practical, except on these very special purpose machines to implement or to design data flow. And certainly commodity clusters or even conventional microprocessors really can't support the data flow paradigm. But when written in a correct way, the Cray XMT can actually support this paradigm of computing, which makes some algorithms very trivial to write, and since it exposes a lot of parallelism, can saturate the machine and run very well and effectively on it. And we've used sort of data flow approach to implement several algorithms, both in scientific computing as well as in graph algorithms using this technique. And so I want to cover both of those, both a scientific computation, which you can write in a data flow manner, and also a graph algorithm, which you can implement in a data flow manner. So you can sort of see the paradigm here, and then hopefully extend that to your problem as well. Okay, so iterative methods are a common way to solve sets of complex partial differential equations. They appear in heat transfusion, radiation transport, all sorts of things. Require sort of an iterative method. And there's this discretization in time and space, in which you iterate over time and then iterate over the 2D or 3D space of the problem in order to solve the equations. So there's typically an outer iterative loop which executes over time. So the state of the system at time t of I is some function of the state of the system at t of I minus 1. And then inside this iterative time loop, there's some loop nest over the dimensions of the problems, so here x, y, and z, in which the value of each of the cell or zone or element or whatever of the system is some function of its neighboring cells. Okay, so if you're doing a heat transportation, you'll fix the boundary values at some temperature or pressure or whatever, and then those will, of course, the values of the boundary cells will then, of course, define the values of the neighboring cells, and as the heat transfuses into those cells, of course, it will then affect the cells that they neighbor on, and then the system will you'll calculate the initial value of the heat at each of the cells, and then you'll iterate over it, and then it'll all smooth out over time in some way. So by setting fixed boundary conditions, we have a start at the boundary. We can figure out the values. We know the values of those boundary cells. We can then compute the values of the cells which neighbor the boundary, and then that simply progresses over space to define an initial value at all the points, and then we iterate over time until we get to some convergence. And so this is sort of like a data flow, right? I mean, neighboring cells or neighboring values define cells define the values of their neighboring cells, and those neighboring cells can compute their value once the value of the neighbors is known. Okay, so logically, it sort of feels like a data flow computation. So here's just what it might look like in sequential code. So here we've got a 6x6 grid, 2D grid. We know we fix the values on the left and bottom cells. So these are our boundary cells, and then the neighbors this cell, the values are all known, so we can compute its value. And then once we have its value, we now know the neighbors of this cell. Since this one were boundary ones, this value has been computed, and we can compute its value, et cetera. Okay. So the sequential code for this simple this fusion equation, which progresses from the lower left-hand corner up to the upper right-hand corner, might look something like this. Okay. So for each cell, I is equal to 1 to n. We take the east value, this one. We take the southeast value, which would be the bottom value here. We take the south value here, and then we compute some, relaxation or smoothing equation, whatever, to compute the ij value. Okay. And so, written in this form, whenever we go to compute the ij value, the other three values, because of the order that the iterations are executed, from 1 to n, and from 1 in I, and 1 to n in j, the values are available, and therefore the new value I compute is correct. Okay, so so that's what the sequential code might look like. Okay, and basically this fills in as a series of wavefronts, right? So the boundary cells are known, and then once I have the boundary cells, I can compute that value. Once I have that value, I can compute those two values, and I can compute those three values, and it just fills in, right? Okay. All right, so there are a lot of computations which are known as wavefront computations, and they start from some initial set of cells, and then they just progress as a series of wavefronts across the space. Okay. Okay. Oh, wait, this slide. Wait. Wait, I left the slide out. Sorry. Okay, so I left the slide out. Sorry. Okay, so if I parallelize this in OpenMP, all right, there are a number of things that that are actually difficult to do, right? So first of all, I've got to write some loop, right, which basically I want to parallelize over the diagonals. Okay, so basically, when I'm at this, sorry, let me go back. I'm sorry, I left the slide. Okay, so I have to write this computation in OpenMP, right, as a series of diagonals. Okay, so I have to have an iterative loop which basically runs from 1 to the number of diagonals. Okay, so 1, 2, 3. All right, and then once I have that outer iterative loop, which is running across the diagonals, then within each of those diagonals, I can compute each of the blocks in parallel. Okay, so I have an outer loop which runs from across the number of diagonals. The number of diagonals is like 2 times n minus 1. All right, and then I've got some diagonal index I, and then from that I have to compute the number of blocks along that diagonal. And once I have the number of blocks, then I can write a parallel loop over those number of blocks. And then I have to figure out which block I am and where I start and end, and then I can compute all the elements within that block in parallel. Okay, so I end up with like 4 or 5 nested loops, of which the outer one, of which the second one is parallel, right? The one that's running over the number of blocks in each of the diagonals. So it's not very easy, right? It's 4 or 5 loops, and it's pretty complex to get all the indexing correct and get everything right. So it's just not something that's easy to do. But if you get it all right, you can get some fairly good performance as long as your block sizes are appropriate for your caches and your L1 and L2 caches, so that when you bring a block in, you can compute all the values on it and then kick it out. Okay, so that's the slide I left out. All right. So wait, this. Okay, so I'm sorry. Oh, I see what I did. Okay. So this slide here should have had that OpenMP or MPI code, and instead I duplicated the XMT code. So okay, well, I'll fix that. Okay, so wavefronts on the XMT are actually very easy to compute, all right, and very easy to program. All right, basically, what you need to do is wait for your neighbors to complete. Once your neighbors have their values, then you can read those values and compute your value. All right? Okay. So the way you do that is to use these synchronized read and write operations that we saw at the end of the last few slides in the last lecture. All right. So basically, by using the full and empty bits, I can provide the single word producer-consumer synchronization I need to implement a wavefront. All right. So the first thing I need to do is I need to purge the cells of values so that when someone goes to read it, it'll see the purged value or the empty value, and the read will not complete. All right. All right. So for those neighbors for those cells whose neighbors have computed their values, those read operations will complete. Okay. So you do a read FF of your neighbor cells, okay, which forces you to wait till they compute their values. Once those values are computed, those read operations will return. You compute your value. You then write your value as a write EF operation, okay, which sets the value and, in some sense, unpurges this operation here, cancels this operation, allowing your downstream neighbors to compute. All right, so that's a little confusing, but the code is actually quite simple. Okay, so this is almost identical to the sequential code. So all you have to do is you start by adding a loop, a doubly nested loop, which runs from 1 to n across I and j, and it simply purges each of the values in this F array. Okay, so if we go back, okay, to here, right? So for I from 1 to n and for j from 1 to n, I basically purge or empty these cells. The Fij value, I set those bits to empty. Okay, so now each of these cells, the value is empty. All right. Okay, and then I simply take my sequential code that I had before and change each of the read operations into a read FF. Okay, so here I read the east value, here I read the southeast value, and here I read the south value. Okay, and until those cells have written their values, these read operations will not complete. Okay, they'll just simply hang out there waiting for those cells to complete. Okay. So for that first cell that was in the lower left-hand corner was neighbored only by the boundary cells, these read operations will complete because those cells were never purged, and so those values will be there. Okay, so those values will be read. That cell will then compute its value, and it will write its value, reading a write empty full operation, filling its full and empty bit. Okay, once that full and empty bit is filled, oops. Went the wrong way. Okay, so let's go back here. Okay. All right, so now this cell here, when it goes to do its 3 reads, will find the bit filled. Those reads will complete. It will compute its value. It will write its value, filling its bit. Okay. This cell will have read this value because it was never purged. It will read this value because it was never purged. And as soon as this cell here writes its value, that read will also complete. It now has its 3 read operations. It will then be able to compute its value. It will write it, fill its bit, which will then cause this cell to be able to execute as well, right? And so simply by using these synchronized read and write operations, this thing just fills in a very natural way, right? Okay, so that's a good question. Okay, so so you do have to be a little careful here. Okay, all right, all right. So the way the exit, so do notice though here that because I'm using these synchronized read and write operations, the compiler will not know that these loops can actually execute in parallel, right? Because it'll think it has all this synchronization, and you set the synchronization up just to be right. So here's a case where you do have to use the assert parallel fragments. All right. So now to your question. So the XMT, the compiler will organize this work in a certain manner, right? I mean, it's got a set static way in which it organizes the threads, right? So the threads that, the way it organizes the work is to take the, sort of the first loops, right? And those are the ones that get scheduled first, all right? So the first iterations here that will get scheduled will be for, I is equal to 1, and then along that bottom row, these j values will get scheduled, okay? And then once those are done, then I equals 2 will get scheduled, and I equals 3, and I equals 4. So the threads that are sort of on the queue, right, will be, I11, I12, I13, et cetera, okay? So you do have to be careful, right? I mean, you do have to be careful that you've sort of organized the loops in the order in which, they will naturally complete, right? If I had written this as, j is equal to n minus 1, j greater than 0, j minus minus, right? Then the problem, what I'll get is a lot of threads that can't complete being scheduled, and then they'll wait, okay? And if you have preemption, right, if threads wait too long and then they get blocked and put off on a block queue and then other threads will get retried, right, you'll suffer a lot of overhead, but, the computation will eventually complete because it will eventually find threads that can execute, right? So to avoid that overhead, yeah, you do have to be a little clever and organize your loops in the order that things get filled in, okay? So, here I've got a nice sort of two-dimensional structured array, and so I know the way it'll fill in. If I've got a, irregular application, an adaptive grid or an irregular grid in which, I've got weird boundary conditions and things like that. For example, there's the ASCII benchmark heat, which is an unstructured grid. So there, what you have to do is you sort of have to sort the cells, right, and make sure that the boundary cells are the first ones, and then the neighbors of the boundary cells are sort of the second ones in the list. And you don't have to get the sort perfect because obviously you can certainly have some threads stalled without suffering much overhead, but you sort of have to get it close, right? That's a good question. And in fact, I've got an example of that later. Yeah. Okay. So that's sort of a way to do, sort of a grid problem in which you can use Dataflow to, fill in the operations. But really notice that, this code is really identical, right, to the sequential code. So if you've got a sequential code which does basically a diffusion operation of some sort, it's really very trivial to change that into a parallel code on the XMT. Just slap, these two pragmas in there, and then you just change these, readFFs, or these reads into readFFs. In fact, recently, I took a fairly complex C++ code that did medical imaging relaxation, and simply by doing that, I had a nice parallel code in a matter of hours.
So the question, what does F and EF
I'm sorry? Right. So this stands for read when the bit is full, and leave the bit full. So it allows for multiple readers, okay? And write EF stands for write when the bit is empty and leave the bit full, okay? And then there's a read full and empty, read FE, which is read when the bit is full and leave the bit empty. So that sort of locks it, right? Okay. All right, so let's look at graph algorithms as another source of where I can use Dataflow. Yeah. Okay, so the bit is full, right? I mean, originally, right? If I don't empty the bit, it'll be full. So just like in sequential programs, if you don't initialize a variable and you go to read it, you'll get garbage, right? Well, here, you'll also get garbage, right? It's not like just because you haven't initialized it, the bit is empty and it'll sit there and wait. You'll get the garbage, right? So the normal loads and store operations, they don't look at the bit, right? They just simply return whatever value is there, okay? So if you want to, do this synchronization and you want the readers to wait until the writer has written something, then, right, you have to purge it, okay? Now that's if you, okay, that's if you just declare things as int or double, right? The XMT actually does support a data type which is sync. So you can declare things like sync sync space int or sync double or sync whatever, right? Okay, and the default for sync is, I think, full or empty. I don't. When originally you think it's empty? Yeah, I don't remember. But even though the XMT programming model supports the sync type, I would suggest never using it, because the trouble with the sync type is that every time you read or write, you're going to affect that bit. Okay, so if it's a sync type and you read it, you're going to empty that bit. All right, and you can get into very subtle things. You know, the most common one is, let's say you've got something that's of type sync, and you read it in a conditional, right? So you do something like of the form, if a of I is less than 0. Okay, that read operation, which is implied by the if statement, right? Because you've read a of I in order to compare it to 0, right? That will empty the bit. Okay, all right, and then you have to fill it later, or the next read of a of I is going to hang. All right, so declaring things sync is very, you got to be really, really careful, because there are all these sort of subtle, ways that you can read values and write values, which can create deadlock. So, I highly recommend not using the sync data type and doing everything explicitly. That way, you sort of can't screw it up. But you can still screw it up, but it's more obvious. Because if you're accessing through pointers, right? You can access a sync variable through pointers, and you're going to empty that bit. So you got to be really, really careful.
I just would like to ask, what's the purpose of that data for or this sense, for example? What we are trying to optimize?
So two things. Oops, let me go back. Okay, so the first thing I'm trying to optimize is, high productivity, right? So for example, if I've got sequential code that looks like, so I've got some sequential code that looks like this, right? And now, I want to parallelize this, all right? I can go off and try, read about how to do this in OpenMP and try to get those, loop structure all correct and things like that. But, much easier for me to simply put, assert parallel, and then read FF, write EF, right? I mean, I make 5 changes and I'm done, right? So, that's a whole lot easier than trying to figure out the block structure and things like that. So there's certainly a high productivity in being able to take sequential code like that and parallelize it. Yeah.
Do you mean that you are going to read and write of matrix elements for each matrix element you are going to use full MPD?
Yeah.
I think that overhead will be very
Now the full and empty bit exists.
Yes, I understand.
Right.
But probably you are going to involve threads with more than just single iteration of loop for a lot. I mean that you are going to compute blocks of this matrix for each thread.
Right.
And then to trigger this operation, you need just only one full MPD cell, not cells in each portable cell.
Right. Okay. So you make a point, right? I mean, oops. So you make a good point. I mean, you
It's an actually produce one implementation cell for each block.
right. Right. It is sufficient to use, one synchronization per block, but then I have to rewrite this loop in terms of blocks. Yeah. Right. That's right. So that's more work. So, I didn't want to show this, but, to get best performance, really what I want to do is to parallelize, assuming it's a big enough problem, right? I really only want to parallelize per row. Okay, so in a production code where n is a big number, I just really parallelize this loop here, this I loop. Okay, and then so now I'm guaranteed that when I go to compute this, since the J loop is now serial, okay, I know that when I go to compute this value here, I only read, this value has already been computed, okay? So in that case, the read of the east elements would be just a normal read, right? But, I could still write that as a read FF because if the bit is set correctly, right, that read operation is still going to come back immediately, right? So it doesn't really cost me anything to represent it as a read FF, right? It's still a single cycle at the processor because it's a single instruction. That'll go out to memory, the bit will be set, the word will come back immediately, right? So there's really no cost at testing that bit in memory. Okay. All right. And the other thing that that I can save here is here each of the operations is identical in terms of time, right? But in a complex system, I may have different materials, I may have different operations I want to do in the cells and things like that. The cells could be of different sizes and shapes. So I can get all these load imbalance issues. Balancing that in terms of block sizes and this and that to make sure that each of the threads or processors in a conventional system get the same amount of work can be difficult. While here, I don't really have to worry about it, right? Because the threads that pick up the simpler cells will execute quicker. They'll go off. They'll get more cells, and and hopefully the whole thing will sort of balance out naturally. I don't have to do sort of a pre-assignment and hope I get it right. Okay. All right. So let's look at graph problems. So here too, we can use Dataflow in a number of different instances to simplify problems. And graph matching is again a very common algorithm that comes up in a lot of bioinformatics codes. It comes up in a lot of partition codes that partition graphs. Comes up in when I'm trying to figure out systems of linear equations, partition systems of linear equations, and etc. So just the definition of a matching, it's some subset of the edges so that no two edges in M are incident on the same vertex. So here's a matching. Here are two edges, and these are the edges. The nodes, have common nodes, right? So here's another matching, and here are a bunch of places where graph matching, comes into play. Okay, so a particular type of matching is known as weighted matching, and here edges have weights. And usually what I'm interested in is finding a set of the edges M such that it's a maximum matching. So in other words, the edges in the set M, maximize the sum of the weights. Okay. So in this case here, the three edges I would want to choose would be this one here for 35, this one here for 20, and this one here for 20, giving me a total of 75. While if I naively chose this one and then this one, which would include now nodes 1 and 3, 4, and 5, this is the second heaviest edge, but then that would force me to include this 10 edge here for 2 and 6. That would give me a total of 70, right? 35 and 25 is 60 and 10 is 70. So that would not be a maximal matching. So obviously the greedy algorithm, which simply takes the next heaviest edge weight, can lead to a suboptimal solution. Now, of course, this makes this problem, I think it's VE squared or something like that to get max. So it's not NP complete, but it's still pretty computationally complex. And if the graph is bipartite, so I have a set of edges like all men and then a set of edges all women, the maximum weighting problem is known as optimal assignment. So each man tries to marry their most preferred woman. If that woman is available and chooses that man, then they get married. If not, the man or the woman has to go choose their next best choice, and so you end up with this maximal optimal assignment problem. Okay, so so there are some polynomial time algorithms which can provide a maximal matching. They use something known as augmenting paths. They're just computationally complex. They take, I think, VE squared or something like that. So they're the approximate. So typically in practice, people use approximate algorithms. They're faster. They're certainly much easier to parallelize, and they usually give good enough results for practical problems. So usually what's used are these approximate algorithms for fast matching. And they're all sort of based on this concept by Hopmans here. And the idea is that you've got a graph of nodes. Each node sends a request along its preferred link. So here 1, its preferred link is to match with 3 because the weight here is 15, while it would prefer not to match with node 2 because the weight is 10. And node 2 prefers to match with node 3 because the weight is 20. So it too sends a message to node 3. Node 3 prefers to match with node 2 because the weight here is 20 and not 15. So it sends a message to node 2. Okay, so at the first step, 1 sends a match request to 3, 2 sends a match request to 3, 3 sends a match request to 2. So now 2 and 3 realize that they have exchanged match requests, which means they're happy with each other. So so then they match and send refusals to all their neighbors, okay, or anyone who sent them a match request, okay. So 2 refuses 1, 3 refuses 1, and then 1 now tries its second best edge, which is 10. Having been refused by 3, it now tries to match with 2. And when it sends its request to 2, of course 2 has already been matched, so it sends a refusal as well, and then 1 remains unmarried, as it would be. Okay. So this is sort of it's sort of a greedy algorithm, but not quite. You can see how you can parallelize this pretty easily. You choose your best mate, you send them a request, and then that mate, either sends you a request back or not. And if you get a match, then you're done. And if not, you try your next best choice. Okay. The trouble with this is that it requires, if you try to implement this, it requires a lot of locking and unlocking and synchronization of the requests and things like that. So typically what's done are queues are produced and nodes are, requests are put in queues, and then those are shipped across the machine, and other ones look at the queues to see who requested them, if it's the same as them, and then if there's a match, they take themselves out of the queue. If not, they put themselves back in the queue with their next best thing. And so you get a lot of these, you got a lot of iterations. It tends to converge slowly at the end because people are trying to find their matches. And you just get a lot of overhead creating and uncreating queues. So the iterative algorithms don't work too well. Okay, but fortunately, we can use full and empty bits to solve these problems as well. Okay, all right. So wait, I think this. Oh, this is just the. Wait, let me flip through this for time. Hold on. Okay. Okay. All right. So let's just get to the Dataflow version. All right, so a typical graph structure looks like this. This is what I was answering the question. So a graph is simply a node. So graph is basically an array of nodes. Each node is a structure. There's an ID. Typically, we store the number of neighbors for that node as an integer value. Maybe the weights of each of the edges or to each of the neighbors is represented by an array of weights. And then the index of each of the neighbors is another array which stores the neighbor list. Okay. So if I'm at node 5, I can quickly look at the number of neighbors for that node and then jump to each of the neighbors of that node simply by accessing or reading this neighbor array. So this is a very typical structure that we use to represent graphs. And typically, in order to optimize our algorithms, this is something that's that the MTGL libraries and things like that you really can't do because they don't know your particular problem. But typically, we'll sort the neighbor list here in either in terms of maybe the index values or the weights or something, right? So that we have fast access depending on the particular algorithm that we want to execute. Okay. So in the Dataflow version, basically, we're going to implement this idea of I'm going to send you a signal if I want to match, and then if you send me a signal back that you want to match with me, we'll match and we'll be done. If not, I'll go ahead and choose my next neighbor. Okay. All right. So I declare an array of signals. Okay. And there are 2 signals per edge. Okay. Okay, and we set the signals to empty. Okay. So basically, I create an array, which is 2 times e, where e is the number of edges, all right? And I set all those those elements to empty. Okay. All right. Then, okay, I write a parallel loop for all the nodes in the graph. Okay. I basically want to set the signal at my edge that I want to match. Okay, so here 3 will want to match with 1, so it's going to set the signal here to 1. Okay, so fill the bit, right? Okay, and once it's filled this bit, it's then going to go and try to read this bit. Okay, and it'll wait until 1 fills this bit, either with a 1 or a 0. If 1 fills this bit with a 1, okay, then 3 knows that 1 wants to match with it, and it's done. Okay. If 1 fills this bit with a 0, okay, then 3 will know that 1 has refused it or has matched with someone else, at which time it will then go and try to, it will choose its next best neighbor, in this case 2, and fill this bit with a 1. Okay. And so in this way, this whole thing will simply just fill itself in. Okay, so this is the first step, all right? So 3 has filled this bit with 1. 1 also wants to match with 3, so it's filled this bit with a 1. And 3 has filled this bit and has tried to read this one. It waits until this one gets filled. It gets filled with a 1. So 3 knows that 1 wants to match with it. 1 knows that 3 wants to match with it, and they're done. Okay, meanwhile, 4 and 5, 4 has filled this with a 1, tries to read this bit. 5 eventually fills this bit with a 1, too, because it also wants to match with 4 because it's its heaviest neighbor, 25. And then these 2 will read, each of them will read the 1s. They'll know they want to match, and they're done. Okay. Meanwhile, 2 here has chosen its heaviest edge, which is this edge to 4. It's 20, right? That's more than 10, 5, or 15. So it's filled this bit with a 1 and has now tried to read this bit, but this bit's still empty, so it's just going to sit there and wait. Okay, and 6 has done the same thing. It's filled the bit on this edge with 5 to 1, and is sitting here waiting for 5 to fill this bit. Okay. Once you match, or once you get a request, or once you've read the bit you're waiting for, if it's a 1, you're done. You know the other node has matched. And if it's not a 1, if it's a 0, okay, then you need to go read somebody else. Okay. So once you've read a 1, you need to fill all your other edges with 0s, okay? So 1 here has read a 3, knows that 3 has matched with it, so it needs to fill this bit here with a 0 and this bit with a 0. 4 and 5 have matched, so they'll fill this with a 0, this with a 0, and this with a 0. And hopefully you get that, okay? All right, so now 2 has been sitting here waiting for something to appear on this link, okay? Eventually 4 fills it with a 0, okay, or sets it to a 0. 2, then that read completes. 2 says, oh, 4 hasn't matched with me, so now I'll go try my next nearest neighbor. That's this link here, 15. So now 2 will fill this with a 1. It'll go to read this. This has already been written, so it'll read the 0, say, oops, 0. In which case it will now go and try its next neighbor, which is this one here, 10. It'll fill this with a 1 and then try to read this value over here. Okay. So let's see. Okay, I get that. Okay. Then I get that, and now everybody's matched, right? These guys are matched, these guys are matched, and these guys are matched, okay? So, you know, this is sort of filled in nicely, right? All right, so now going back to your question is, how do I organize this so that the threads that get scheduled earliest are the ones that execute first? Okay, so here it's a little bit more complicated than it was in the graph algorithm, in which I know, you know, that I just need to go from 1 to n and I'm done, right? Okay. Oh, okay. So, so here's actually the code. Okay. So to make sure that this thing actually executes correctly, I have to sort by the number of edges. I have to sort by the weight of the edges. Okay. So if I sort by the I know that the first edge it's always going to complete is going to be the heaviest one, right? Those two nodes will choose each other, marry, and complete, okay? So in order to make sure that this thing progresses in the right order, I just have to sort the edges by their, by their weight, okay? So I do that, and then, you know, for the heaviest weight edge with the heaviest weight, which will be the last one, NE, to 0, I simply, for each of the edges, I set the signal to 1, and then I try to read the other signal, okay? And if the other signal is a 1, I break, because I'm done. If not, I'll choose another edge, okay? And then for the, when I get a 1, I know I have to set the other signals to 0, the other edges to 0, okay? All right, so, you know, again, you know, just with a couple of write EFs and read EFs here, you know, I can parallelize this thing and it just fills in nicely. Okay. Okay. So this is the idea that because resources are limited, the data flow must be scheduled more or less in the order that the edges will execute. And in this case, it's, you know, by weighting it. So, you know, sometimes you do have to sort of think of the right way to, you know, structure these things and so that things fill in. Okay. Okay, so we do that. Okay, so now there's still a problem, okay? And this is where you can sort of, I didn't want to put this in here, but because I wanted you to sort of feel good about this and think about this as a good way to write programs. But there's another very subtle problem that ends up happening in this case. So I've sorted things by weight, so the heaviest weight edges will go first. And so those are guaranteed to complete because those nodes will choose each other. But there's still another subtle problem that happens and can actually cause deadlock in this case. And when I wrote this problem, I had this done in like 3 hours, and I ran it on a bunch of graphs, and it worked well. And then I ran it on a really big graph, and it deadlocked. And it took me 3 days to find the deadlock. Okay, so that's sort of the bad news. Okay, so consider a situation here where I have 3 processors. Okay. All right, so the first 3 nodes that will execute will be, you know, 1, 3, and 4, right? Okay. So you know, these will be the edges. This edge will be picked, and then that edge will be picked, right? Okay. All right. So now 1 and 2 will match, right? And 4 will still be scheduled, right? But it's going to pick, but its next edge is 5 and 1, right? Okay, but the heaviest edges are, 15, this edge and this edge, all right? So I can get to a situation where all the active threads, because their best spouses have been chosen, right? They all now, their next choices have very low weight edges, all right? So if the graph gets big enough, all right, I can get to a situation where all the active threads, their best spouses have been chosen by other people. Now they look and they have very low weight edges. Okay, so you can get into a situation with this problem, right, where the threads that are scheduled, the nodes that are active, have very low weight edges, even though you've structured things so that the heaviest edge weights first, right? Just because the heavy ones that they wanted to choose were taken, so now they've looked at their next best choice, and they're all very low weight edge things, okay? In which case, all your active threads are basically waiting for other ones to complete, and they never get scheduled, all right? All right, but there's actually a very simple solution to this, and that is that instead of having an edge sit there and wait, okay, if its neighbor that it wants to choose hasn't been scheduled, simply to do a recursive call and go ahead and schedule it and execute it itself, okay? And so the fix is simply, basically I ask, has this neighbor of mine, is it being processed? And if it is being processed, then I can simply wait. And if it's not being processed, so if the neighbor active is 0, I simply do a recursive call and process the neighbor itself, okay? That way, then, whether or not the neighbor that I want to match with has been scheduled or not, it'll get executed, okay? All right, so basically with the data flow operations, there are two things to worry about. One is to structure the order of the operations more or less in some way that the data will fill in, okay? And the other one is to, if you look at something that needs to be executed, to go ahead and jump to it and execute it yourself in a recursive call so that you come back and eventually execute yourself. And with those two solutions, they're simple things to, just have those in the back of your mind when you do a data flow solution or a data flow program, and you'll avoid deadlock and race conditions. Okay, all right, and that's that. So I don't know if I convinced you to try to use data flow, but it really is it's a nice technique, and if you get comfortable with it, it can really simplify your life a lot. And on the XMT, it really does work very, very well. So maybe there'll be some opportunities tomorrow for me to work with some of you on trying some of these techniques. Okay, thanks.